Hello everyone, this is Dr. Madhavi, Professor of Mechanical Engineering in MVSR Engineering College, Hyderabad. My colleague, Mr. K. Karthik Rashekar, Assistant Professor of Mechanical Engineering in the same college, and myself, today are presenting a topic from kinematics of machines in computing mechanisms of machinery. This is treated as lesson number 1, and the contents of this presentation are taken from Kinematics of Machines by Ronald T. Hinkle. The presentation is mainly designed for undergraduate engineering students. The contents are mechanisms, mechanical computing mechanisms, and applications. Starting with the fundamental concept of a machine. A machine is a mechanism or a group of mechanisms to perform useful work. Then what is a mechanism? Mechanisms are devices designed to produce specific constrained output motions. For example, a watch is a mechanism. The stored energy in the spring is used to overcome friction and move the hands. Here, no external work is done. Now, trying to understand the computing mechanisms. Firstly, we'll identify the types of computers in general. They are analog and digital. Analog computers are particularly adaptable to continuous solutions and may be constructed for virtually instantaneous response. Computing mechanisms with these analog computers involve some operations such as addition, subtraction, multiplication, division, trigonometric functions, resolution of vectors, integration, and differentiation. In this lesson number 1, here we are considering 3 important mathematical operations. One is addition, subtraction, the other one is multiplication, division concepts, and the third trigonometric function. The other mathematical operations will be dealt in lesson number 2. Now coming to the first algebraic operation, that is addition or subtraction. Some form of differential mechanism is used universally for adding and subtracting 2 variables by mechanical means. 2 basic types in this particular differential mechanisms are link and slide differential, bevel or spur differential. So if x and y are 2 variables given as inputs to the mechanism, then we can derive an output W as x plus or minus y by 2. For example, let us take case by study. Case 1 will take simple differential adders. Now you can see a 5-link kinematic chain. In this 5-link kinematic chain, as a rule in kinematics of machines, a kinematic chain can be converted to mechanism if at least one link is constrained or fixed. At least one link has to be fixed and motion to be given to some link in order to obtain a predictable motion or path. Now in this mechanism, let us say this is a fixed frame we have fixed, that we can call it as link 1. So you have link to a bar and link 3 also a movable bar. So link 2 and link 3 are movable links or movable bars. And you have link 4 is another movable bar, which in turn is connected to link 5 rollers. Link 5 rollers. So the link 2 and link 3 will act as guides to this link 4 over the link 5. Now here, scales are fixed for each link, link 2, link 3, and link 4 in order to measure the displacement of these links under the given conditions. Now, going back to the schematic sketch of this mechanism, X and Y are input links. They are differential displacements. X and Y are differential displacements given to link 2 and link 3. Then we can obtain W as X plus Y by 2, as X plus Y by 2 on link 4. And you can measure the same on the scale, fix it to link 4. We can see the animated motion of this particular link and slide differential. The top and the bottom bar, which are link 2 and link 3, are moving away from the fixed link frame 1 with a differential displacements of X and Y. And we can notice the output bar, that is link 4, moving away from the fixed frame to a displacement of W, which will be X plus Y by 2. So this is how a simple mechanism can be designed for an algebraic addition. Now let us go to case 2, that is linkage differential. That is considering here a slight modification in the previous step. The link 5 were in the previous case study taken as a roller, fixed to link 4. Now that link 5 is now replaced with a slotted link 5. Is replaced with a slotted link, which is called link 5 this one. You have slots over here as well as here. And link 2 and link 3 are placed inside the slots so that they can move freely inside the slot, here and here as well. Then link 4 is again a pin jointed to this link. All the links 2, 3, and 4 are made to move on guided rollers here in order to ensure the alignment in its translation motion. Now here again you give X, Y as a differential displacements from the fixed frame and measure the output W as X plus Y by 2. This particular can be derived using the simple triangle method, similar triangle method. Okay, you just drop a perpendicular from the link 2 onto this base and then join this inclined line. You form a triangle, two triangles. This is the two triangles, smaller triangle and the bigger triangle. Left, if the distance between link 2 and link 4 is equal to link 4 and link 3, then you just take the ratios of the sides of these particular triangles, similar triangles, you can obtain W is equal to X plus Y by 2. Here we can see the animated motion of this slotted link again. Here where 2 and 3 are given X and Y differential displacements, and observe that link 4 is having an output displacement of X plus or minus Y by 2. Now let us go to case 3. Case 3 is again another linkage differentials. In this particular case, there's again a modification in the previous mechanism. The modification is again in the link 5. Link 5, instead of making a slotted link, here we are joining link 2 to link 5 with a pin joint. Here, link 2 and link 3 and link 5 with pin joints. And there is another additional linkages here attached to this particular mechanism, that is sliders. A slider is attached to this point. A slider is attached to the link at this point. This is to ensure that this motion here is on this path. However, because of the pin jointed motion, pin jointed link of link 5, there is a flexibility in link 2 and link 3 for a rotational motion, to happen here. Okay, now link 4, which is the output link, is again pin joined to the link 5. Now the same exercise is done here, that is you give a differential displacement x and x here, y here, and because of this differential movement, you can notice that 4, which is ensured and alignment is properly done through these guide rollers, is made to push forward and moves to w is equal to x plus y by 2. However, the problem in this particular mechanism is an error of epsilon value will be introduced to the output value. So the pin joints are substituted for the sliders on link 5, and the angularities of links 2 and 3 will introduce an error in the sum. This is mainly because of the angular motion, small angular motions of link 2 and 3. The error will be introduced in the output. You can notice it better in your animated motion. You can see how link 2 and link 3 are moving on the guideways. And you can see that the link 2 and link 3, as the motion is moving towards right, you can see them coming out of the straight motion and taking some angular rotation. Because of this, an error is introduced in your output value. Now this is case 4, in linkage differentials. Now you can see now another modification in the previous mechanism. That is, link 5 is now brought to forward, not at the end, but brought forward and directly attached to link 2 and 3. You can see the sliders on link 2 and 3 are on opposite sides of link 5. So the sliders connected to link 2 and 3 are placed on the opposite side of the link 5. Got it? Now, the input sliders are put on opposite sides of link 5, and because of this, the errors that occur due to the angularities of link 2 and link 3 will compensate each other provided. So that's the advantage of this particular system of arrangement of the mechanism. So you can reduce that epsilon value. Now let us again, based on a similar triangle concept, you can consider the output value using the ratios of these particular triangle values. Then you get W is equal to Bx plus Ay by A plus B. A and B are the distances between 2 and 4 and 4 and 5 respectively. Then if A is equal to B, then your W becomes X plus Y by 2. X plus Y by 2. So this is how you can go for the calculation of your output value in this particular mechanism. Now let us see the animated motion, how this motion happens for you to get the values and compensate the error, nullify the error in both the cases. Because one becomes plus epsilon, the other becomes minus epsilon, and that gets cancelled, giving you a value of W is equal to X plus or minus Y by 2 as an output value. Yes. Another interesting application of the adders, that is bevel gear and spur gear differential, mostly used in automobiles. Now let us study first in the bevel gear special differential. The top figure, this is a bevel gear differential. And this view is the top view of this particular bevel gear differential. The bottom one is the spur gear differential. Now I shall explain in detail the bevel gear differential mechanism. Here, gear C, D, E are set of bevel gears fixed to an arm, through an arm, and these are the output shafts. Now your gear F and B are input gears. Input gears. Okay. Now let us understand the working mechanism of these gears. Suppose to start with, for a kinematic mechanism, it is essential that you fix one link. Now to begin with, let us fix gear C. Let us fix gear C. Okay. Now once you fix the gear C and give input to F, X motion. In this here it is angular rotation. Okay. Angular rotation. Now, if you can calculate the instantaneous center for this particular X, this point can be OCD, is the instantaneous center. Now, if you draw a triangle here again, if this is the X displacement, then the center arm position will be X by 2, because if this is entire thing is capital D, then this will be half of the diameter, thereby this value being X by 2. So the ratio of these gears will be, if this is X, then the motion on this will be X by 2. Now similar exercise you do by fixing this gear side E, and give rotation to Y. Now once you give rotation to Y, then the arm rotation will be Y by 2. Now if you add these two, it will become X plus Y by 2. So that's how the bevel gear differential operation takes place. You can see a photograph of this bevel gear differential. Here you can see these rings, internal gear, bevel gear combination here. Similarly, you have it on the other side, and this is an arm connection member. Okay. There comes the next important mathematical operation, that is multiplication and division. The simplest multiplication to mechanize is multiplication of a variable by a constant. Let C be a constant and xy be the variables. Then you can say y is equal to C into x, which is the simplest form of multiplication value, which can be easily obtained, which may be done by a gear ratio equal to the required C for rotary motion or by a simple lever system for straight line motion. The problem of multiplying two variables is more complex. Okay, the form of equation is xy is equal to C into W. So you are trying to multiply two variables, then the problem complexity will increase. This mechanism provides a theoretically exact solution and may be constructed to permit both variables to change algebraic sign. A similar triangle method of performing this multiplication is shown in this. It's a very interesting mechanism, linear motion mechanism. It's again a 5-bar kinematic chain. You can notice this here. This is a frame. Link 1 is a frame, you can see. It is a fixed frame. Then link 2 is this vertical link, and it can have a x direction motion. Then you have link 3 here, which has this y direction motion. It can move top to bottom in y direction. Then you have link 4, this one, an inclined portion here. And this link 4 is pivoted at this particular point here. This point is taken as a point of reference for the entire mechanism. Fixed pivot here, so that this link 4 will have a small rotation about this fixed point. Okay, this link 4 now is again connected to link 2 and 3 through a pin here, and also to link 5, which slides up and down on the rollers, is also pivoted, pin jointed here. So now you can understand the motion of these particular links that are arranged here. Now let's see the distance from the fixed frame of reference to this bar which rolls up vertically. Okay, that C is a constant value. Now X is one input, displacement input, Y is another input that is given to this link 5. So X and Y are given to link 2 and link 5, and they are linear translations and variables. Okay, they're not constant and not uniform. Then link 3 will give you the necessary output displacement. Link 3 will give you the necessary output displacement, that is in this vertical axis, as W as xy by c. So the W value here is the product of two variables. The product of two variables. So in order to obtain the product of two variables, this is one type of mechanisms that we can design. Now this W is equal to xy by c can be obtained from a similar triangle concept again. Okay, you just draw some triangles here on this line, on this four positions, from here to here position, and try to indicate these x, y, w, c positions in order to obtain the ratios of w by y is equal to x by c and w is equal to xy by c. Now let us see the animation motion of this particular linear motion mechanism. You see the inputs are given to this x and y simultaneously, but differential translation. They are given simultaneously, but differential translation. And this motion through this link is carried to this link. And now this link will give you the output motion as W, which is equal to xy by c. Xy by c. Going to another interesting linkage in this same multiplication values, that is cam follower linkage. Here you have two pairs of cam followers. Okay, let me explain. This is again 11 chains, kinematic chains. The number one is fixed frame, which is not shown here in this particular figure, but one will be a fixed frame, a board. Now, link 2, look at link 2. Link 2 is a cam. Okay, this cam is an eccentric object, obviously. It rotates about an eccentric center, which has an angular rotation of x value. Okay, then link 3 is, what you can see here is, link 3 is a follower. Follower moves up and down in vertical direction. Okay. Then you have link 4, a slotted link connected to the follower 3. Okay, connected to follower 3, as well as another follower on the other side. Now, link 5 is another bar which is connected to link 4, and one end of this link 5 is connected to a spring to hold its position. Now, link 4 on the other side, you have link 6, which is again another cam, an eccentric center operated link, which rotates, which has a rotations of y. And 7 is a follower, which has a translation motion of up and down. Right. Then you have link 8. Link 8 is connected to link 5, here, link 5. Okay, and the other end of link 8 is connected to link 9, which is a common link for 8 and 10. But link 9 is allowed to move in an anti-lock cam slot. In an anti-lock cam slot. This is an anti-lock cam slot. It is allowed to move in that particular. Why? Because to obtain the desired output, we do this. Then through link 10, here, link 10, you connect this to link 11, which is a slider. This link 11 slides in a grooved slot, grooved slot. So the link 11 will give you the final output W, which is the product of two variables. So let me explain you how it works. Now coming back to this, CAM2. The CAM2 rotates with a very small angular rotation or motion, X. Similarly, CAM6 is given angular motion, Y. So angular motions X and Y both are not same, they are different, and they are given to links. You can give them in the similar direction or in opposite direction. So once they are done that, so the respective followers are displaced from their position in vertical direction. So the link 3 and link 7 get displaced. The displacement of follower is logarithmic motion. It's a logarithmic motion, that is log x. Link 3 displaces in log x direction, and link 7 moves in log y direction. Okay, then what happens? The output of these two is derived at link 5 as half of log x plus log y. This is the actual output of these two. That is half of log x plus log y. But our interest is not in terms of logarithm, but our interest is in terms of multiplication of two variables, x and y. So in order to obtain this, that means you have to eliminate this log term. You have to eliminate the log term. In order to eliminate this log term, you allow these links to go inward in an anti-lock cam slot. Okay, inward to anti-lock cam slot. And this anti-lock cam slot will again allow the link 10 to have a motion reciprocating through link 11, and thus obtained W is equal to X into Y. You can see this and pictorially in this particular mechanism. See, if you can see that your X, both are having same motion, X and X. Both the cams are having same motion, then you can see they are different here. X, Y are different here. And you can see the sliders having a motion of X into Y. There is a certain demerits in this particular mechanism. Neither variable may be permitted to reach 0, either X or Y, or negative values also not permitted, because the log of 0 is indeterminate. The trouble will ensue if the value of the variable becomes less than 1. Since beyond this point, the log becomes negative. So the value answer what you get is redundant. If such conditions are unavoidable, the method still may be used in the design if both sides of the equation can be multiplied by a factor so chosen as to make the minimum value of the variable always greater than 1. For example, if I want W is equal to X into Y, where Y is in between 1 and 5 and X is in between 0.5 and 3, then we multiply both sides of the equation by 3. So you get 3W is equal to 3X into Y. If I can take logarithm on both the sides, then it becomes log 3 plus log W, which is equal to log 3X plus log Y, and the cam becomes actually a log 3X cam. The answer taken from the anti-log cam is clearly 3W, but this may be accounted for in choosing the scale factor of W. So that's how you can handle this particular mechanism for a multiplication of two variables. There's a third category that is called trigonometric functions. The continuous trigonometric functions, that is y is equal to sine theta or x is equal to cos theta, may be generated over any portion of the entire range of theta from 0 degree to 360 degree with a Scotch yoke. Now the displacements what you are giving are not just numbers, but it's the functions of trigonometry. Let us say capital radius r is of rotating arm determines the scale factor of the device. Look at this Scotch yoke mechanism. In a Scotch yoke mechanism, you have a crank of capital R radius rotating about a pivoted point here. The other end of the crank is connected to two links. One is in horizontal position, the other one is in vertical position. And these two links are in turn connected to bars, okay, which slides in one in horizontal and the other one slides in vertical direction. Now, if you arrange these two in perpendicular direction this way, or it need not be perfect, this thing, angle, one can be theta dash and another can be theta, not necessarily 45, but it can vary from that. Then you give input to this crank, okay, small rotations in this crank, then this pin will try to push forward and this motion of this one will allow the bar to push outward this direction. Similarly, when it is moved in a different direction, this motion of the crank will push the bar to upward direction. The displacement thus noted in horizontal and vertical directions are x is equal to r cos theta or x is equal to r sin theta dash. Similarly, y is r sin theta and y is r cos theta dash. Now let us see the motion of this. You can see very clearly how the crank is pushing both the links, both the bars simultaneously in x and y direction. X and y directions. And the displacements thus noted are in the trigonometric functions. Now, another interesting mechanism, a sun-planet mechanism, that is Gare sine cosine mechanism. Here you are using both trigonometric functions simultaneously. Now let me say the bigger circle is a sun planet, that is capital R. The smaller one is the planet Gare, which is having a radius of small r. A crank connects these two. This is the crank connecting both sun and the planet. Now this, if you put connect another link, okay, at this pivoted at this particular point, you can notice that this point C will have a cycloidal motion. A cycloidal motion when this planet is having a simple harmonic motion inside the sun Gare, inside the sun Gare. So the cycloidal motion will have both cosine as well as sine functions within it. Let us see some mathematics of this. A pinion of radius small r is equal to capital R by 2 measures with an integral Gare of radius r. Now when the pinion is rolled on the integral Gare, a point C on the circumference of the point pinion will trace a hypocycloid. So the equation of a hypocycloidal R, x is r minus r cos theta plus small r cos r minus r by r theta. Similarly, the y displacement is r minus r sin theta minus r sin of r minus r by r theta. For the special case of r is equal to capital R by 2, the equation becomes very simplified version, that is x is equal to r cos theta and y is 0. Y becomes 0. You have only an x translation. These equations show that C moves horizontally with simple harmonic motion. As I said, the point C on the vertical link will have a simple harmonic motion. You can have a very clear pictorial view or animation of this particular mechanism within the structure. You can see how the planet Gare rolling inside a sun Gare is having a simple harmonic motion, and while the point C can have, that is the bar motion, is having a cycloidal motion value. I can show you very clearly in this more transparent of the crank motion with respect to the sun and the planet, and the point C having a horizontal motion of cycloidal motion. So this is a photograph of a sine cosine mechanism, sun planet mechanism, which you can operate it for different motions. Now, the interesting one is you still have some discontinuous trigonometric functions. Still can have that. The trigonometric functions y is equal to tan theta and y is equal to cot theta are called discontinuous at certain points in the range of theta between 0 degree to 360 degree. No geometric device or any CAM mechanism which will mechanize the full range of these functions. It's not possible to have this particular displacement values of x and y in tan theta and cot theta to entire 360 degrees motion. A CAM designed to mechanize a portion of the range of one of these functions must have a very steep slope as it approaches the point of discontinuity. CAMs that cover a considerable range, say 0 degree to 80 degree for the tangent, must have a large average radius and a very small total throw to keep the pressure angle within practical limits. The result is a very small scale factor output. Look at the mechanism. You have, bar on a roller moving in a horizontal direction, and there is another crank-like link which is pivoted here, and this is a fixed pivot, and this link rotates in this plane, and due to this connection with this link 1 through pin, bar 1 reciprocates in to and fro in x direction with a displacement of x is equal to a tan theta, where a is the distance between the link 1 to the fixed point position. Or it is also a cot theta dash, where theta dash and theta are the angular positions of this particular link to with respect to horizontal and vertical plane. You can see how the linkage is. So you can get this only intermittently, not continuous. It's a discontinuous trigonometric function that happens, and it has its own applications in a mechanical engineering or in any mechanisms of different applications. So thank you very much. Thanks for listening to this. Very soon we come back with lesson number 2.